some talk on mathematical modeling. So I am especially working on mathematical biology, and my area of specialization is mathematical modeling of complex biological interaction. I mean, I especially work on the biological interaction of species, and I especially use the tools such as nonlinear dynamics, chaotic theory. All these tools I used in my research. So in this talk, I especially focus on mathematical modeling. I especially focus on the mathematical modeling of biological system, and more precisely, I will focus on the modeling of prey-predator interaction. So if we talk about mathematical modeling and what is mathematical modeling, so it is just representation of real world systems, representation of real world system into mathematical models, that means into mathematical equations. So if we look into our earlier classes, into our earlier life, we have been solving many problems related to real world. Hello?
Yes, you are audible, please.
Yeah, okay. So we are solving many problems in our life. For example, like the problems of simple interest, and the problems of height, distance, and there are many problems we are solving from our childhood. So if we see to the formula of the principal interest, so it is the relation of three quantities. The relation of this is the relation of time period, interest rate. So we formulate a particular real scenario into mathematical equation. So this mathematical equation is usually known as mathematical model. So mathematical model usually represents the real scenario of a real world problem. So actually I would like to share my screen here. So in this talk, I'm going to discuss about the concept of mathematical modeling. Then I will cover some basic knowledge about, cover some information about nonlinear differential equations, and how we solve these nonlinear differential equations, because it is very well known that the solving nonlinear equations is not very easy. And then I will discuss about some models of differential equation in biology, and which represents the real world scenario. So as I discussed before, that what is mathematical modeling. So mathematical modeling is nothing but it is just a representation of real world system into mathematical equations and mathematical formulas. So especially what mathematical modeling do? So it models a real world problem into equations, and then we apply some tools, some mathematical tools such as linear algebra, numerical analysis, and some other tools to examine the behavior of the system. And this behavior of the system is very close to the real behavior of the real problem. For example, if we see the climate dynamics, and in these days we are observing that the climate forecasting is very predictable, and it is very informative for us. Like there are we can see many in many times this gives us a forecasting, and we use many assumptions to prevent from it. So mathematical modeling is a description of a system using mathematical modeling, mathematical concepts, and mathematical languages. Especially a mathematical model helps to explain a system and to study the effect of different components of real world system, and it make predictions about that particular behavior of the system. So we perform experiments and we solve real world problems, which are definitely, if we go to the real world system and we go to perform some analysis, we go to collect some data, we go to field, then it is definitely it is time consuming, and it is very expensive. So mathematical model gives us a way to reduce our time and to reduce our expenses. So studying many various type of problems in scientific research and some industrial problem, and like such as the development problems and the manufacturing, mathematical modeling is very applicable. So these are some areas where we generally we use mathematical modeling, this, such as the environment, as I say, the environment prediction, and then population dynamics. Definitely the population dynamics, because this is about the change of population in time, and the other environmental factor. This is the study of population dynamics, climate modeling, economics, war-related problems, such as this is the we can say the optimization operation research is a very best example for war-related problems, and it is also applicable in medicine and biology. And it is as a broad area in physics, aerospace, space technology, seismology, material research, and many other things. So if we see, so these are very well-known mathematical models that, for like Newton law of motion, F equal to ma, mass energy equation equal to mc square, and Pythagoras theorem, c square equal to a square plus b square. I think these three models are known to everyone, and these represent some real-world scenarios. So here I'm going to discuss about the what is the process of mathematical modeling. So here in this graph you can see there are some steps, there are some process of mathematical modeling. So first process is problem statement. So in this process we have to first figure out the problem. What actually is the problem? What we need to do, and what is the problem behind the real world phenomena. So if we discuss the problem statement, then we have to think about these three things. The first one is the interest of the problem. That means this is what is the area of the problem. It may be some customer related problems, it may be some ecological related problems, it may be some uh, some some physical related problems. And then we consider, we will find out what are the points which are incomplete. That means what are the point, that means which have to include in the problem. That means we have to find out the variables, concept, relations, restrictions, goals, and what are the priorities. So especially this comes upon the mathematical model. So for the, it is well known, for the mathematical model we need some variables, we need some restrictions, we need some relations, and we have to figure out our the goal and the priorities. Definitely the priorities matters. So then we come to the theory. Then after finding the problem, making the model, and configuring the variables, then we will apply some theory. So which type of theory? It may be any mathematical theory like dynamical system theory, it may be linear equation, it may be optimization techniques. So we will apply some mathematical theories to predict, to solve the equations. Then definitely here literature review also matters. So now we will apply some numerical methods, because we have modeled a mathematical equation, and the equation is of the nonlinear type. Then definitely it's solving it is not an easy task. So we have to apply some numerical techniques, and after applying numerical techniques or a numerical technique, it may be some software, it may be MATLAB or some OD problems for numerical analysis. So we could apply any mathematical tools. Then there is a program. Then after numerical methods we will come to the program. So program, what it consists of: flow diagrams, implementation, user interface, and the documentation. So then after doing all these steps, definitely we will come to the report. What is the report? In report, we will find out the description of the problem, analysis of the problem, what we have done, what is the what we have done, and what are the results, and then we compare the result to the real world phenomena, and we examine whether this result is feasible or not. So feasibility of result gives us a motivation to model more appropriate real world system. So, and one more thing here, the limitations. There are some certain ecological parameters or some physical parameters which are not easy to model. So there are also limitations in the mathematical models. So after comparing the results to the real world output, we can say that, okay, this model is very relevant and this model represents this particular, the situation of this particular real world problem. So now I will discuss the types of the models. So here there are especially 5 types of model. So there are some linear models, and definitely there are some nonlinear models. There are some dynamic and static models, continuous and discrete models, deterministic and probabilistic models, and in other sense we also call them stochastic models, and then explicit and implicit models. So what is linear and nonlinear? In, if I say in general sense, so a function which satisfies principle of superposition is known as the linear function. So similarly, a model which exhibits linearity, that means everything is linear. If we see the graph of the model, then if it seems to be linear, then we can see the model is linear, especially, and definitely if we are talking about linearity, then the variables of the model should be of degree 1. That means it should be degree 1. If you are talking about the linear, that means it should be of degree 1. Then we can say, okay, this is the linear model. So a linear model uses some parameters, constants that make the relation between one model, one variable to another variable, because there may be possible that in that particular model we have more than one variable, so we should have some relation between that model. So, and what about the nonlinear models? If we talk about the nonlinear models, so if any model have nonlinear scenarios, that means a model of it, we talk about the function, if any function have the variables with more than 1 degree, then we can say that this is a function of type nonlinear type. So if we see into real world phenomena, what is linear and what is nonlinear. So like if I am giving just a very simple example, like we wake up in the morning, and everything is constant in our mind. We are thinking happily, we are happy, and we take our breakfast, and we go to the college and something doing best. So at that situation, our mind is in linear form, and suddenly something, there is a fight with your friend or something negative happens with you, then your mind has many thoughts. It has a non-linear thoughts. So dealing a person with non-linear thoughts, I mean in agree, if he is angry, so dealing and person who is angry is not easy. So you have to wait for, this is the reason, this is general difference between linear and nonlinear. If I say into ecology, so linear means we have everything okay, and suddenly the rains start. So this is nonlinear nature of the environment. So definitely. So if we have something nonlinear phenomena, if we have something in the form of nonlinear and we want to solve it, then we have to convert this nonlinear system into linear system. So we have some theories for converting this nonlinear system into linear system, and then definitely we have some mathematical tools to solve linear systems. So now we have some static and dynamic models. Static models means the models which are time invariant. That means a model which have no impact of time. That means time does not impact on the system, and a model which has impact on time. That means the system which is dependent on the time. Then this type of model is known as the dynamic model, such as the growth of a plant, population change. So if we formulate models, then we can of the how dynamical models. So if we see into dynamical models, so dynamical model are especially of the form of differential equations. That means it may be a equation or it may be a partial differential equation. Now I came to discrete and continuous models. So a discrete model treats objects in a molecular model. So if you we have studied
Hello.
discrete. Hello. Okay, I think it is okay. So the discrete models are modeled by differential equations. Differential equation in which the solution of next step depends upon the previous step. So, and if you talk about continuous model, so definitely a continuous model depends upon a are modeled by differential equation. There is a continuity such as the velocity of a flood, electric fields. These are the examples of the model which are represented by real world phenomena. And what is the deterministic and probabilistic model? So if any model has some variables, and if the variable is in the form of probability distribution, that means there is any randomness in the model, in the variables, then we can say this is a stochastic or probabilistic model. And if any model has no randomness, it is continuous in nature, then this type of model is known as deterministic model. So deterministic model, we can say, is a form of continuous models. So all the models, continuous model, are the deterministic models. So now I will, as I know, as I already said that I am I am working on the differential equations and mathematical model of biology of differential equations. So I will cover some basic topic of differential equations. So here there are especially two types of differential equation which I study. One is ordinary differential equation and second one is the partial differential equation. So ordinary differential equation contains at those two variables where one variable is dependent variable and second variable is independent variable. And definitely partial differential equation are the equations which have more than two variables, in which maybe one variable is dependent and more other two more variables are independent variables. Definitely the ordinary differential equation in the real world phenomena are most important differential equations. We use these equations in population change, velocity change, for calculating acceleration, velocity, and if we apply the PDs, so especially if we see the change in space and time, that means the change in time also in space, for examining such systems we use partial differential equations. So here, and then there is a linear and nonlinear differential equations. So if any differential equation has degree 1 and if it's a dependent variable and its derivatives not multiplied together, then definitely it is a linear differential equation. And if dependent variable has degree greater than 1 or it is multiplied by with its derivative, then we can say this is a nonlinear differential equation. Definitely here there are some examples of differential equation. Here first, this differential equation is a linear, and I think this is a very well known concept. So I'm skipping uh, this slide. So now, as I say, if we have any nonlinear system, so it is very important to linearize the system. So if we want to deal the system, then we use some techniques to linearize the nonlinear equations. So for example, we have any system of this form dx by dt equal to f of xy. This is system which depends upon t. Just imagine that t is a independent variable. So here fx is a nonlinear system. So for this system, and we want to linearize the system, so first of all we have to find out a equilibrium point, a point, a area of interest point where we, at which point we want to linearize the system. So for example, let x star and y star, the interest point where we want to linearize the system. So for linear approximation, we use Taylor expansion theorem, and we expand this function f of xy with the help of Taylor expansion at the point x star y star. So when we expand it, and because we need a linear system, so I ignore the higher term system. I only consider the linear terms. So here after expansion, this dx by dt can be written as in this form: f of xy plus derivative of x with respect to x at point x star y star, and this term, and then derivative of f with respect to y at point x star y star, where if we see it to point x star y star, so this x star y star is the constant solution of this function f xy. So from dynamical system theory, a constant solution of a dynamical system is said to be equilibrium point. So we can say f x star y star is said to be equilibrium point. And if it is a constant solution, then definitely the function at x star y star is 0. So if we take f star y star equal to 0, then this equation is approximated to, this goes to 0, then we have this term and this term here. So here we can see we have a nonlinear system, we have nonlinear function of fxy, and we apply Taylor expansion, and we find dx by dt approximated to this, and this seems to be, this is a linear term. So we have converted a nonlinear function into a linear function. This technique is generally known as the linearization, and we use it by and here you can see the perturbation. Here x bar is the perturbation, x is a variable, and we perturb it by some quantity x star, which is equilibrium point. So now, I am going to discuss about a system of equation. We have system of equation. We have two equations, and we assume that x star y star is equilibrium point. That means f of x star y star equal to 0, and definitely g of x star y star equal to 0. Sorry, I missed here. This is g of x star y star equal to 0. So we apply Taylor expansion theorem, and here we expand this function and this function, then we will get similarly, definitely from here we will get of this form, and f of x star y star equal to 0. Similarly for g, it is g star x star y star equal to 0. That means we are going to find only these terms. So here, putting this 0, we have this linear system dx in the form of this linear system for dx by dt and dy by dt. So here we can see this is also in the linear form, this is also in the linear form. So now we can write equation 2 into vector form. So here we take dx by dt equal to jx. J is the Jacobian matrix. This matrix is known as Jacobian matrix. J is Jacobian matrix, and x is the vector here, x and y.
What will happen here?
So here we
I
can
need to
see,
move from A to F, or I need to calculate the simple path. Then what I will do here, I need to move like this. So here I move from A to F. So here I need to calculate the simple path. So I need to move from A to F. So here I need to calculate the simple path.
hello. So now if I directly want to calculate this Jacobian matrix, if I directly want to calculate Jacobian matrix, so this Jacobian matrix is, we have a function f, we have function f here, and this, we have function g here. So if I directly want to calculate this Jacobian matrix, so the first component of matrix is the function f, the derivative of function f with respect to x, and the at point x star y star. Similarly, the second component of this Jacobian matrix is the derivative of function f with respect to y, and this component, this j21, this is calculated by derivating function g with respect to x, and this is calculated by derivating g with respect to y. So this is very easy. This is very, we can easily calculate Jacobian matrix. Now there is a question: what does this Jacobian matrix tell us? So I mean, what does the linearization tell about the original system? So if we have linearized the system, okay, we have now linear system, and now what is the relation between this linear system and the original nonlinear system? So for this, we have to consider, we have to find out the behavior of the original system. So the behavior of original system depends upon the eigenvalues. Definitely we have this eigen Jacobian matrix, then we have its eigenvalues. So the behavior of this linear system depends upon its eigenvalue. And it is important to notice that if the system is unstable, then definitely original system is also unstable, and if this system is stable, then original system is also stable. So this is the main reason behind why we linearize the system. A linearized system gives us the real scenario of original system. So if we have eigenvalues and we are able to calculate these eigenvalue, and then we have some scenes, we have some scenarios on eigenvalues. So if all eigenvalues are non-zero real parts, then we can say the equilibrium point. This what we have calculated here, x star y star, because we are interested to find the dynamics of the system at point x star y star. So we can find the behavior of the system at this equilibrium point. So if the eigenvalues at this equilibrium point are non-zero real parts, then we can say, okay, this is a hyperbolic equilibrium. And if the eigenvalues are non-zero real parts and they are negative, then we can say the system at particular equilibrium is stable. That means if we make a small perturbation, if we make a small change nearby its equilibrium point, then after some time it will come to again that particular equilibrium point. So that means there is no impact of perturbation on the stability of the system, and this is such equilibrium is known as the node. Now another scenario, when any of eigenvalue becomes positive. If any of eigenvalue becomes positive, then the system is unstable, and if they are opposite sign, that means one eigenvalue is positive and one eigenvalue is negative, then it is not, we can say this is unstable and this equilibrium is of saddle point. And now there is another scenario. It may be happen that we will find some imaginary roots, imaginary eigenvalues. Then if we have imaginary eigenvalues and its real part its real part is negative, then we can say it is a stable limit cycle, or sometimes we say it as a focus. And if any real part of this imaginary eigenvalue becomes positive, then then we can say this is unstable equilibrium. So I am going to take some example of linearization, and then I will examine the behavior nearby equilibrium points. So let we take this example. This is a system of equations. Here dx by dt equal to 2x minus y minus x square, dy by dt equal to x minus 2y plus y square. And so we need to find the equilibrium points. So I said the equilibrium points are the constant solutions of the Appl system. So substituting dx by dt, dy by dt, we can get the solutions. We can get the equilibrium points. So after calculating this, we found 2 points 0, 0 and 1, 1. And we calculated Jacobian matrix. So how we can calculate? So this is say this is function f, this is function g. So derivative of first, this term is the derivative of this function with respect to x. So here you can see derivative of here 2 into x, this is 2 minus here 2x. Similarly, now this term is the derivative of this function with respect to y. So here we can see this goes to 0 and this one is minus 1. Similarly here this is this term is the derivative of second function. This is g of xy with respect to x, and here we have 1, and again we have this term, this component is the derivative of this function with respect to y, so we can find minus 2 plus 2y. So we have Jacobian matrix, and it is very easy to calculate. So first we check the behavior of Jacobian matrix at 0, 0. So we put 0, 0 here. So as I put 0, 0 here, so Jacobian matrix at 0, 0 is calculated as, so definitely this goes for 0, this goes for 0, so we have minus 2, 1 and minus 1. And if we compute its eigenvalues, so we have these eigenvalues. We can see this is plus minus root 3. Definitely the eigenvalue is real and opposite signs. So as I have discussed earlier, if the eigenvalue of any Jacobian matrix is real and opposite signs, then it is known as the stable. That means the equilibrium is not stable. Now again, if we calculate the Jacobian matrix at the point 1, 1, this is the second equilibrium, and if calculate at 1, 1, then we find here we can put 1, this goes to 0, similar minus 1, here 1, and here again 1, 1, then again goes for 0. And we can easily compute its eigenvalue, and eigenvalues are 0 plus minus I. So here we can see the real part of eigenvalue is 0. So previously, hello?
Yes, Dr. Mishra, you are audible.
Yeah, okay.
You are audible.
There is some notification in my screen, like the host has asked you to start your video. Maybe what is this? Host.
Let me check.
I have notification.
Okay, you are sharing your screen. That is enough. I mean.
Yeah, okay. So I will. Okay. So we have.
Yeah, please, go ahead.
Thank you very much. So here we have two eigenvalues, and they are imaginary eigenvalues, and the real part is 0. So here we can see the eigenvalue shows the rate change of trajectories, and here the rate change of trajectory, here real part is 0. So always there is a center. That means the trajectory do not change. So this such type of equilibrium point is known as center. So now I will come to the application of these nonlinear differential equations into biology and ecology, and I will see how this linearization and how this tool which I have discussed previously are important and are applicable in real world phenomena and real world problems. So in differential equation is used in population growth models, prey-predator interaction models, and very well-known infectious disease models, fishery and wildlife models. Definitely, it is it is very applicable on the tumor growth and cancer disease models, cell movement models, and law dynamic models. So I will discuss some of the models in my upcoming slides. So, so first of all, what is population growth model? I would like to discuss about it. So population growth model describes the scenario, the change of population in time. So like if I take example, so there is any city, its population in 1990 was 1 crore, and then after some year it becomes 1 crore 50 lakhs, then there is a change in population in time. So with the help of these population growth models, we can find out, we can examine actual rate growth of the population, so that it could help us to find the population after some years. So here there are, and these population growth models are widely applicable in species interaction. So because we live in an ecosystem, and in ecosystem all the species are related with a food chain, and if there is any species is in danger and they extinct due to some reason, then definitely we have also some impact of that impact of the extension of that particular uh, species. So the sustainability of the ecosystem is very important. So as we know, we are linked with the food chain in this ecosystem. So the dynamics of animal is also very important to study. So mathematical models in ecology discuss about the dynamical behavior of the ecological system, and the dynamics of the biological species depends upon many factors such as growth, death, intraspecies competition, and there are many other biological components in which the species depends. So first I will start with just growth of the species. So here I consider, let n is the population of any particular species, and dn upon dt, then differently dn upon dt represents, sorry, here I have taken p, so let's take p. So p is the population of any species, and if dp by dt represent rate change of population of that particular species in time, then definitely 1 by n, 1 by p dp by dt shows per capita rate change of population. So rate change of population depends upon per capita birth rate and per capita death rate. So if we consider per capita population growth equal to birth rate minus death rate, that means 1 by n, 1 by n d, what, sorry, 1 by p dp by dt equal to b minus d. If b is the birth rate and d is the death rate, then definitely we have equation dp by dt equal to rn, rp. So where r is b minus d, that means this is equation of dp by dt equal to rp. This equation is known as the exponential growth model, and if we look at its solution here, its solution is dp of t equal to p0 e to the power rt, where r is the growth rate and p0 is the initial population. So if we see, it's, let's say here is somewhere p, here is somewhere p0, and if r is positive, then definitely it will go, it will increase exponentially in time. If time will increase, then it will also increase. And if r is negative, that means the population growth is negative, then definitely if here somewhere here is the p0, then after some time it will converge, it will go to the zero population, because t tends to, if we take here, it tends to infinite, then we have zero. So after for if we have r negative, then after some time, after infinite time, we have population growth zero, we have population zero. And if we have are positive, then there is a exponential growth in the population. Definitely in real world scenario, this is not best, because the exponential growth of any population in real world is not possible. There is restriction. For example, if I take a basic example of a lift, so we have resources, but the resources are limited. So when there is too much population, and there are limited resources, then definitely they make competitions. And due to this competition, there is some loss in the population. I take a basic example of a lift. So if in a lift, the maximum capacity of the lift is 22. So after 22, it becomes constant. That means after 22, it cannot take more person into the lift. So now it is fixed. And if we do that, then definitely there are consequences. There are negative consequences. So similarly, we have limited resources, and we have too much population. Then we have some intra-species competition between the species, and they compete with each other, they fight with each other, and there may be some loss. So models for modeling this phenomena, we have very realistic model, which is known as the logistic growth model. Here, logistic growth model shows a real world scenario that for some time the population grows, but after reaching to carrying capacity, it saturates. And this is obvious in natural phenomena, because there is a carrying capacity of every individual, and there are limited resources. So definitely after some time it goes. Here you can see there in time there is a increment in the population growth, and then after reaching to its carrying capacity, here it goes for saturation and it becomes constant. That means now the population growth above k is not possible. So this is the most realistic growth model, and it is widely used in prey-predator interaction, in tumor growth models, in many other models. So here it is the solution, and it is well known that because it is a population, so it has to be positive. So then k by p0, k is carrying capacity, p0 is the initial population, it should be greater than 1. So now I will come to some real applications, and I will describe some prey-predator models. So I'm taking a very basic example of prey-predator models. How do we formulate such models? So just think, there is a habitat. It may be a jungle, it may be some area, some lake, some forest, it may be something. So just examine, there is a forest and there are two species of prey and predators. So there are two species and prey and predators, and look at the scenario when there is no predator. When there is no predator and there is only prey. So in this scenario, there is no destruction in the population of prey due to the predation. So in this scenario, prey will increase. In which manner? For more realistic scenario, we can take logistic growth model or exponential growth model. So here this function fx, this function fx models the growth of the prey. Sorry, here I missed something. This is dx by there is mistake in the slide. This is dx by dt and dy by dt. Sorry, this is mistake. So the change of x population over time. So the change of x population over time when the predator, just imagine the predator is not available. So that the change of prey over time can be modeled with any of this growth model. We can take exponential or logistic growth model. Then if predator interact with prey, now if predator interact with prey, then definitely it will attack on prey and it will consume. So this function gx here, this term represents the encounter of prey and predator, and this function gx represents number of available predator, number of available prey for per predator in unit time. So this function gx represents the food density, how much food, how much prey are available to for the food of the predator, and this term represents the encounter term for the prey and predator. And here now I came to this equation. Here this is dy by dt. I'm sorry for this. This is t. Dy by dt can be written as minus y minus d plus this one. So here we have assumed that the death rate of predator is proportional to its density. So the death rate of predator is proportional to its density, and this term represents the profit. This term represents the profit on the population of predator. So here, so this is just a model where two species are interacting, one prey and one predator. Definitely there are models with many prey and many predators, but here I will discuss on only two species models. So here the fx is represents the per capita growth of prey population, gx counts the number of prey consumed by predator or number of food availability, and d represents the death constant, death rate, and gx definitely here it is in plus because there is a profit on the prey population due to the predation. So here now I will take a basic example of Lotka-Volterra model which counts two population, the population of rabbit and foxes. So let x represent the population of rabbit and y represents the population of foxes. So here dx by dt says the rate change, the change in population of rabbits over time, and dy by dt says the change of foxes over time. So just consider the population of rabbits and foxes, and there are only three ecological components have been considered. First component is the growth of prey, then predation, then growth, the profit due to predation, and the death of predators. So here we have in this Lotka-Volterra model, it is assumed that the prey in the absence of predator, prey grows exponentially. So here dx by dt, it is the exponential term. So this represent ax represent. So here fx is equal to 1. So this ax represents the growth of prey in exponential manner. That means there is no restriction in the growth of prey. And then we have another term b of xy. So here b of xy, y, this represents the encounter function, encounter of prey and predator. Here y represents the population of predator, and x, here fx equal to x. That means here all the prey are available as the food because fx equal to x. So all the here this fx equal to x represents that all the prey are available as the food for the fox. So here now here in the equation operator we can see dy by dt, that means population change of foxes over time is due to profit in the predation. So this term and the rate of profit is c. So this term here we have in positive term, and again there is a death rate, there is a mortality there is a mortality of foxes. So we subtract this term minus dy, and this term represents that uh, mortality depends upon the number of predators. So here and always it is important to notice that because we are talking about the population. So population, initial population now. So here now we solve this system and we examine the dynamics of this system. So here first of all we need to examine the equilibriums. So for examine equilibrium we will substitute this equation equal to 0, that means dx by dt equal to 0 and dy by dt equal to 0. So substituting these equation equal to 0, we found two equilibrium points. First one is 0 0 and another one is this one. And now if we want to find we want to examine the dynamics of the system, then we have to calculate the Jacobian matrix at that particular equilibrium point. So I have done it here directly. So I obtain this eigenvalue here, eigenvalue at 0 0 equilibrium point, and the eigenvalues are here. This is the Jacobian matrix calculated at 0 0, and the eigenvalue is a and minus d. So here it is, you can see the eigenvalues are real, but they are opposite sign. Real and the opposite sign. That means this equilibrium 0 0 0 0 says that there is no prey and there is no predator. There is no prey and there is no predator. So this equilibrium says that the system without prey and predator is unstable. That means if we put a single prey, if we put a single prey in the habitat, then it becomes unstable. That there is possibility that they will evaluate. There is evolution on the population of the prey and the predators. So that means this system is unstable. That means there is a possibility that always there is no extension. There is possibility that the population of prey or population of predator may have evolution. Now we have another Jacobian matrix which is calculated at this equilibrium point. So at this equilibrium point, hello. So we have Jacobian matrix at this equilibrium point. So this is calculated as in this form. This is the Jacobian matrix, and its eigenvalue is plus minus I root AD. So here we can see that the eigenvalues are complex conjugate and its real part is 0. So again we have center and we have limit cycle. Here it is important because I have already previously I have discussed that if we have conjugate, we have complex roots and then we have limit cycle. So it shows that the system with this equilibrium is limit cycle. So limit cycle means in a mathematical point of view, a periodic solution of a dynamical system is said to be a limit cycle. So here now I have made some numerical simulations here. I choose some parameter values. They are real in nature, and I choose some parameter values. A is here growth rate of prey. You can see here is the growth rate of prey. B B equal to 4 by 3. This is the rate of predation. We can say this is the rate of predation. And then C and D are taken as 1. So C represents the profit, the conversion of prey into predator, and D represents the death rate of the predator. So for this system, I have made simulations, and I have observed here. You can see in this first figure, the green curve, this green line represents the population of foxes, and this blue curve, this represents the foxes of rabbit. So you can see here there is fluctuation. There is fluctuation in time. So after some time, there is a repetition of same period's solution, and similar happens with the population of fluctuation. So it is not actually, this is not only mathematically. There are some authors, there are some biological papers, they have reported that prey predator relationship is a periodic. That means after some time, after some years, there may have same number of population of prey and predator in a particular habitat. This is biologically proved. So here again, this is phase protected space, and here we can again say I have changed the parameters. I have changed the value of B here, and for different value of B, I observe the periodic solution. So as here, we have seen that for all value of A and D, we have always periodic solution. So taking any value, we will always have periodic solution. That means here for this Lotka-Volterra model, particularly the parameters like birth rate, death rate, rate of predation are not impactful on the dynamics of the system, on the dynamics of such prey predator system. So here this is the biological scenario, and there are many researchers, they are working in this field, and this is right now this field is one of the most famous field in mathematical biology. So now I will discuss some other important aspect of differential equation, and this aspect is the modeling of SIR disease model. So SIR disease model, like it is right now we are fighting with the pandemic coronavirus, and we know that there is at least there are three situations. There are some population they are susceptible, then there are some population they are infected, and there are some they are recovered. So during a pandemic, in an infectious disease model, these three populations are basic. Maybe there are some other biological factors, or there are some other ecological components which could be added here, but I am going to discuss only after taking these three populations. This is basic SIR model, which is applicable in most of spread disease modeling. So here, this imagine a situation when there was first case of COVID-19 in Wuhan. So there are only susceptible and infected peoples. So imagine there are ST is the population which are susceptible, and that means which may be infected, and IT represents the population of infected peoples, and RT represents the population or recovered people at some particular time t. That means it may be after then 10, then 20, then 30. That means all these population are defined at particular day. So just take after some day 100 days. After 100 days, there is some situation, and so here we are going to talk about the rate of spread, how this disease spread one individual to another individual, and what is the impact of the parameters on the spread, and how we can completely remove these pandemic from our society. That means we need a society with disease free. That means we are interested here to find out a disease free equilibrium. So for this, to this end, here we imagine these assumptions, and here the whole population or of that particular city is represented by the ST plus IT plus RT. That means number of susceptibles, number of infected, and number of recovered people. So here, so rate change of susceptible peoples depending upon time, it depends upon the interaction of susceptible individuals and infected individuals. Definitely, if susceptible and infected interact with each other, then the susceptible will be infected. Say, then that means there is a loss in the population of susceptible peoples when they interact in infected peoples, and these all, and it is assumed that all susceptible peoples which are infected, which got infected when they interact with infected peoples. So here there is a positive term in ID. That means all the person which interacted with S person are got infected in.
Hello. Hello.
Hello.
Sir, I can't hear why.
Hello. I'm audible there. Hello. I'm audible there. Hello.
Yes, sir.
Okay. So here this is basic reproduction number. Basic reproduction number represents the number of individual which can be infected by one infected people. So here this is R0 beta by mu. So if R0 is less than 1, if R0 is less than 1, then after some time the pandemic will be removed. And if R0 is equal to 1, then it remain and it is stable. It will that means every individual will infect one individual. And if R0 is greater than 1, then the pandemic is increasing. That means after some time there were a lot of infected individuals, which is happening in India. In India, the R0 is 2.8. The rate for the COVID scenario in India, the R0, that means basic reproduction number in India is 2.8. That means every individual is infected at least 2.8 persons. So I take this basic example of Wuhan city. I take that the number of susceptible people at Wuhan city is 1 crore, and at some time the infected people are 13, and I observe that there is no recovery. So only there are infected peoples and only there are susceptible peoples. So I take these parameters. Beta is a rate of interaction, rate of infection, and mu is the death rate. Mu is the rate of recovery. So, and then after I rescale by using non-dimensionalized technique for simplification, and I converted S0 into 1, and I0 is converted by this one, and I make the simulation. And here what I observe that for this simulation, here this represent the susceptible individuals. This represents the recovered people, and this represents IT represents the graph for the infected people. So here we have one people, one, and suddenly for after some time it is start decreasing, and this goes for saturation. And here you can see for 60 days the recovered people are 0, even it is 50 days, and after 50 days they start recovering, and they recovered a lot. And there are also some infected peoples, and you can say here there are some infected peoples between the 60 days to 100 days, and there are also recoveries. So here we can say there that after 100 days, for this rate of recovery and this rate of infection, after 100 days the infected individual will be vanished. That means that the disease will vanish. So that means the R0 here is 1. So that's why the pandemic vanishes in time. So here we can see how this differential equation is important to modeling such phenomena of disease spread. So now this is my final example of love affair models. So this is quite new, and this is generally unknown to many of researchers. This is very limited area. So we know that our emotions, if I go to the biological point of view, our emotions for any particular person depends upon time and their behavior. So if in future, if their behavior changes, then definitely our emotions also changes over time. So here we take equations, two equations. X, say this is any individual, Y is another individual, and this represents the emotions over time, and the emotions, rate change of emotions over time, rate change of emotions over time. So this is what this represents when hello, I'm audible there?
Yes, you are audible, sir.
Okay. So first here I will talk about this term beta 1 y. So that means when this individual is present with X, these assumptions are made by Rinaldi, and the assumptions are when the another individual, another love couple is present with X, then there is a positive growth on the emotions of first individual. Definitely it usually happens when they are together, then always there are positive vibes, and always love may increase. And similarly same thing happens when praise when this individual is with his pair. That means this is the pair, and X is the male, say Y is the female. When a female is with a male person, then their emotion increases over time. And similarly the same assumption has been taken when this is male person is with a female individual, then their emotions are increases, and this shows the rate, the loss in the emotions. So this is the loss in the emotion. Alpha 1 are the positive parameter, beta 1, beta 2 are positive parameter, and what is A1 and A2? These are the appeals. A1, A2 represents appeal of female, to X and means to male, and A1 represents appeal of X to Y, and this shows the rate change. That means this shows the rate of appeals, how much they appeal with each other. That means appeal is also very important factor on the this dynamics on their emotions. So this is very important. Love affair model, definitely there are many things which affect the relationship. There are like there is a triangle models, and there are many models, and there are other components which affect the relationship, but here only these three components are implemented. So this was all about from my talk, and so you can see here how the differential equations are important in real world phenomena, especially in the biological scenarios. So this is very important. Hello.
Yes, you continue, sir, please.
So
you are audible.
Especially the mathematical modeling is very applicable on the interaction of prey species. Maybe there are two prey, one predator models, which has very important, we may have very important properties, and there we can also model intraspecies competition. We can model cell growth. We can model population growth models. Like we can model tumor growth, because the tumor growth is also very important aspect in our society. And if we a very important topic which currently I am working is the movement of cells towards the gradient of the cell. That means if we talk about the prey-predator system, so in prey-predator system usually prey and predator move randomly here and there, and suddenly they found some prey and they attack on it. But in real scenario, if we see, so when they look at some predator, or when predator look at some prey, so instead of moving randomly, they run towards the prey. So this is not a random movement. This is a direct movement. That means this is a direct movement of prey towards the prey. I mean the direct movement of predator towards the prey, and then they run towards the prey and they capture it. And this phenomena is known as the direct prey taxis. Direct prey taxis. This is known as a taxis. But in aquatic systems, this is very new. This is very new research area currently. In aquatic systems, many prey releases some chemicals, and predator detects some chemicals, and they move towards the chemical, and they move toward the chemical, they detect chemical, they move toward the chemical, and they found the prey and they consume. So the movement of the predator towards the chemical is known as the indirect prey taxis. So this is very natural phenomena, and it is usually seen in most of prey-predator models. So thank you very much for listening me.